Hello and welcome everyone. Let's continue the Sean Prazard list by solving climbing stairs. We're climbing a staircase and it takes n number of steps to reach the top. We can take either one or two steps, and how many distinct ways can we climb to the top? We can see from the first example that we have two staircases and we want to get to the top. So drawing a picture, we can see that this is one staircase, this is two staircase, and this is you. In one huge step, you can get to the top. This is one way, or you could start slowly and get to the top, in which case this is going to be two ways. And we also have let's try the second example where we have three. The staircases are three, and once again this is you could start slow and climb to the top. This is one, or you could start slow then take a big chunk of step, and this is going to be one, or rather one, or you could take a big chunk and decide to go slow, and then this is three. But imagine that our staircase we're given five, right? We're given five staircases rather. This is 1, 2, 3, 4, and 5. This could get really complex and confusing in that you could start here. This is 1. You could start 1, go 2, 3, and this get really confusing. This just tells us that we can try something like a decision tree. Should we try that maybe? So this is you here, and you want to get to the top of the staircase, right? The top of the staircase is basically when there is no more staircase for you to get to. But we know that you can take either one stairs or two stairs at a time. Basically, so you're either taking one staircase, in which case you would have two more staircases to conquer, or you could take two staircases, in which case you would have just one more staircase to climb. Again, we can see that you can take, for each step that you've taken now, you can either take one more step, in which case you would have one step to conquer, or you could take two staircases, in which case now you have 0 steps to conquer. Now this basically means that, okay, cool, you're at the top. You're at the top here because you have no more staircase to conquer. Now let's continue with this side where you want to take one staircase and this is 0. You have nothing else to conquer. You've gotten to the top. Hooray, you're at the top. Or you could take two staircases, in which case 1 minus 2 is going to be minus 1. And this doesn't work, right? This is invalid. That means from this point, you can't take two staircases, because it will lead to you falling off of the staircase. There is nothing else. You can't take minus 1. Now we can go back to this final one, and whereby you take one staircase and you arrive at the top again because there is nothing else. This is 0. Or you take two staircases, in which case we have what we previously had here, in which you fall. So now we can see that we have 3 staircases using a decision tree. Now why am I using a decision tree? I am using a decision tree because it is easier to picture a decision tree for large cases. We can't count the staircase for having 5, but we can use a decision tree to picture what we want. Now henceforth, to make it a little bit neater, the left arrow, or the left side, basically we're taking one step, and the right is going to signify that we're taking 2 steps. Also, rather than getting to the 0 case, can we make it better? We see that when we were at 3, we were trying to see when we get to 0 case, in which case when we get to 0 there is no more staircase to conquer and we are good. But if we go beyond 0, then we can't take that step, and we know that that's wrong. Now, rather than getting to 0, is there any base case that we can get to? And yes, there is. We know that if there is only one staircase, if we are given just one staircase and you are asked to get to the top of the staircase, you can take just one step. You can't take 2 because there is just one staircase. If you take 2, then you are definitely going to fall off because there is nothing for you to land onto. So 1 is a base case because 1 stairs gives us 1 step. 2 is also a base case because if you are given 2 staircases, it is clear that you can take just 2 steps at a time, or just 2 steps to get to the top. Either you go slow you take one, or you take a big chunk and you take two. So we know that these two are base cases, whereby you take one stairs to get to the top once in one move, or there are two steps and it takes you two ways to get to the top. No, now continue to our decision tree. Let's move on. Don't forget that our left and our right signifies that we are. So just to start this over and give ourselves more space, we have 5. Left means that we're taking one step. Right means that we're taking two steps. Our base cases are 1 and 2. Cool. So now we can take one step here, in which case would have 4 left to conquer, or we take 2, in which case we would have 3. Now we could take, for each decision now, we could take 1 again, in which case we have 3 to conquer. We could take 2, in which case we have 2 steps to conquer. But our base case tells us that when we have 2 staircases left, then there is only 2 minimum. So at this point, we've got it to an answer because we know that there are 2 steps to take from this place. So we're kind of like good here. Now let's continue with this one. We take one step rather, and we are left with 2, or we take 2 and we are left with 1. In these instances, we are also good because we've gotten to a base case whereby 2 is going to give us 2 movements and 1 is going to give us 1. This is a dynamic programming problem, and to better understand this, you need to understand things like recursion and memoization, because we'll be using that in this problem. Though there's a way to solve it iteratively rather, but this is just a good intuitive way. Comes more intuitively to me, picturing it, than I would rather solve this where I can picture the decision tree and then solve it iteratively. So I feel like recursion is a good base knowledge to know to solve a dynamic problem knowledge. Now this 3 is already repeated here, and we know that having this repetition, this is going to be recursion, is not good for our call stack basically, because now we have to go down this decision tree when we've practically already gone down there, and this is where we need the memoization technique, whereby we have already stored decision tree that we visited earlier. So for instance, if we visited this decision tree, we can store it somewhere, and then when we get to another decision to make, we can just check our storage at storage, have we seen this sub problem before? And then our decision tree is like, oh yes, you have. And then we're like, okay, what's the results? Rather than going down all this path. This is what the memoization technique is for, to store sub problems so we don't have to go repeat problems I've already solved, and that's bad for efficiency. But for the sake of this drawing, we're going to go down this path whereby we take one step, we have 2, we take another step and we have 1. You take one step, we have to take 2 steps and we have 1, and we know that our base cases is going to give us 2 and 1. If we sum this up together, we should have 2 plus 1 plus 2 plus 2 plus 1, 2, 4, 6, 8. So we have 8 distinct ways to get to the top. Now this is the first way of solving this problem, whereby we use our decision tree to traverse, where this approach is called top down rather. We're going from the largest number and we are going down to our base cases. This is recursion and memoization. This takes 2 of n time complexity. This is because for every decision we have 2 decisions to take, and this is just growing exponentially, right? Our decision keeps growing exponentially, but we can shorten this by using the memoization, and then we reduce the time complexity to O of n. We can go from 2 of n to O of n using the memoization. Basically, we won't be taking 2 decisions because it's possible that we visited each and then we're just storing it in a memoization. Now, a memoization. But if there is a way whereby we don't even have to use the memoization technique, we don't have to go down the 2 path, can we try that? And yes, we can actually try that path. And this is the iterative top-down approach, whereby once again we're also going to be considering our base case. And what's our base case? Our base case is one staircase been solved in one way, you can climb one staircase in one way, or we have two staircases and we can climb this in two ways. Now we have 1 and we have 2. If we want to climb 3 staircases now, in our decision tree, we know that if you take 1 or you take 2, then basically you are taking 2 or 1 step. But we already computed this. We already know how many steps we are taking in one way or two ways. So we don't have to compute this again or go down this path because we already have this stored. So what can we do instead? Instead, we just sum up what we have for taking one staircase and for taking 2 staircase, and then we have 3. I hope this isn't confusing. I hope it isn't confusing at all because it might take a bit to wrap your head around. Just let's go over it again. So we know that our base case is 1 and 2. For one staircase rather, you can take 1 step, and for 2 different staircases we can take 2 steps. Now for 3 different staircases, you can take either 1 or 2 staircases. Now instead of computing all this all over again, we can just visit what we already computed, what we already previously stored, and just sum it up together, because these are the ways that we can get to it, and we just have 3. Basically we're climbing up of each other. If we have four ways of 4 staircases, if we're given 4 staircases rather, we know that it is always going to be the sum of 3 staircases and 2 staircases, which we've computed before, so we don't need to compute all over again. Basically we can just get the sum of the last previous computation. Now this is going to give us 6, no sorry this is going to give us 5, and we know that for the 5th staircase, computing this is going to give us 8, which is what we got previously. So this is the iterative approach, and since we're just getting the last 2 computation, we'll be doing this in linear time, and extra space though, because we are storing or saving the last previous value. But there is a way to not store the previous value, whereby just using variables to store them. I'm going to show it in the code, but I'm not going to be coding that because I don't think it's very intuitive, but I'm going to provide it in a code solution linked in the description box. But for the purpose of this problem, we're going to be solving using the recursive approach and using the iterative approach. All right, let's solve the problem. So to solve recursively, since we have a function that will be calling itself, we need to define that function, and we need to define our base case. If n is equal to, basically if our staircase is 1, then we want to return 1. But if our staircase, if we have 2, then we know that we want to return 2. These are base cases basically. Then we want to return, want to call this function on itself, and we want to take 1 staircase plus another chunk of 2 staircases. Then we can return this function. This is not going to run. Okay, yeah, this run. But if we submit it, we should get a time limit exceeded error, like we have here. And this is the case whereby, if you recall when we're talking about memoization, basically this is going to take a while because we are recomputing what we already computed. How do I stop this? Okay, time limit exceeded. So basically we are recomputing what we already computed. Since we have this decision tree, it's growing exponentially, and this is really bad because our call stack is just calling itself over and over again. This is where we use the memoization technique to store it. Now we're going to have a global memo variable, and we're going to say that if n exists in memo, then basically just return the value. Basically, if we've already computed this number before, then we do not need to compute it again. We don't need to compute it again. Just give us back this number. There is a inbuilt function in Python, LRU cache, but I'm using this hash table because I think that some languages don't have LRU cache, and it might be easier for them to understand what's going on using this hash table. Basically, instead of, so we're going to be storing our results in this hash table, and we will be returning this. So basically what we are doing is, this is a, if we are given 5 number of staircases and we go down, we take 1 stairs, this is going to give us 4, or we take 2 steps, which is going to give us 3. Now we are storing each of these value for 4 and for 3 in our hash table, so that if we go down 4 path, eventually when we take 1 step from 4, we're going to visit this 3 again. Rather than solving for 3 all over again, we already have this saved in our hash table. This is what we are doing here, and it's just to solve for efficiency, to make our code more efficient. This is why we are doing this. And if we submit this now, we should see that this runs and we no longer get this time limit exceeded error. Now this is the bottom up, or rather top down, sorry, I mixed up a lot. This is the top down recursive approach. We're going from top to down, like we're breaking it down basically. Now if we want to solve for this iteratively, we can kind of like have an array where we have the base cases. Now why do we have an array of the base cases? You can store this using a variable, but you know that we are kind of like pretending that our array is one indexed here, whereby you are taking 1 staircase and you are doing this in just 1 step, or you are taking 2 steps, or you are giving 2 staircases and you take 2 steps for it. We are not considering what if you are giving 0, because basically that will mean that there is nothing to climb, there is no staircase to climb, staircase is non-existent. So in this our array, we're only considering you are taking 1 step, you are taking 2 steps, and ignoring the 0 index, but that will come in handy soon. Now since we already have the base cases of 1 staircase and 2 staircases, we can iterate over our number. We already have for 2, so we don't need to include 2. We're starting from 2 and up to the end staircase, and we're going to be appending to our array the value of the last 2 decisions. Basically, if this was 3, then we're basically saying that sum the value at the index before and the value at the index 2 steps before, because we can only take 1 step and 2 steps at a time, and we are appending it to this count. And for this array keeps growing to accommodate the number of staircases that we're given, and eventually we are going to return this should be square brackets because we are accessing. We're going to return, if this was 3, if this had grown, if we had finished computing and this is 3, basically we want to return 0, 1, 2. We're still going to assume that the index is 0, 1, 2, and want to return the index at this point. This is what our answer is going to be. This is basically how it's going to be growing. For 3, it's going to sum up the last 2. For 4, it's going to sum up 3 plus 5, which is 5. 3 plus 2, which is 5. For 5 is going to sum up 5 plus 3, which is 8. And basically this is the visualization of what we are doing on line 5 and line 6. Now we can just run this code and see that it works. And once we are sure this works, we can go ahead and submit it. Alright, this is a very good way to practice. This is similar to the Fibonacci number, this problem, and this is a very good way to practice dynamic programming, to warm us up for more complex dynamic programming problems, because dynamic programming problems can get really complex. But I really hope that you understood it. I tried really hard to explain it as much as I could if you had not come across dynamic programming problems before. But yeah, let me know what you think in the comment section below. Thank you for watching this video. See you on the next pattern. Bye.